Hello and welcome back. This is the second part of the videos where we are going to use the Lime package to generate image explanations of complex image classification models in PyTorch. In the previous video, we went over the setups that are required to do so. We downloaded the data of cats and dogs we want to analyze, the JSON file that holds the translation between the class index and human readable labels, and the setups that we need to do to make PyTorch models and Lime compatible. In particular, we downloaded the inception model, converted the class indices to human readable labels, converted all the images to RGB mode with its convenience functions, and then made sure that our images will always be conforming to the standards of inception. That means the image sizes in particular and the normalization of the image. We also needed to write a small predict function that follows the scikit-learn style of creating a prediction for a specific model. And because PyTorch doesn't do this, we need to implement this ourselves. And we stopped the last video with a small prediction test, and we saw that the picture of the dog above was indeed classified with high probability as a boxer. We're now ready and in a position where we can use the Lime package, and in particular we use here the Lime image explainer to generate a local explanation of which parts of the image were important to generate the assignment. So what do we mean by this? A local explanation essentially means that we generate like a replacement or surrogate model. So in order to do this, we need to convert our images and all the models into the standard that Lime expects. And essentially, we need to convert this image into our RGB format, and we need to convert it to a NumPy array. We need to have the classifier that takes this NumPy array and produces probabilities. This is what we used the predict method we've implemented above for, so that we can use the scikit-learn style interface. The top labels are the predicted explanations for the top n outcomes, and then we need to tell the Lime package the number of samples it should use to generate this local explanation. If you have a more powerful GPU available, a good value is about 1,000 samples. Here we use 100 because we only run on a CPU in this example, but it still generates useful output. So we create an instance of the Lime image explainer here. And what we want to do is create a specific instance of our model. So we need to transform the image into a NumPy format. Here we call the predict method we have implemented earlier, and we look at the top 5 labels, and here's the number of samples that Lime is using to create the local explanations from. Now what we want to do is to overlay the image of the boxer in our case, and overlay it with the regions which are most important for the classification result. So we only look at the positive contributions, so like the boxerness of this specific image. Technically, we do this by producing an image mask, and then we overlay this, and this is where we use the mark boundaries function on the scikit image package for. In the first step, we only look at the features, as we said, or the parts of the image that made the model think that this is a boxer. And this is done by using the parameter positive only equals true. So we generate this mask from the explanation we have generated here. So we get the image and the mask and use positive only equals true and take 5 features and hide the rest equals false. And then we can use the functionality from scikit image to overlay those boundaries. And this essentially is like the boxerness of this image in the view of the inception model. And you can see that with our domain knowledge, or rather our everyday understanding of what a boxer looks like, that this makes sort of sense. You also notice that the image is slightly distorted because we need to convert the image into the format Inception Network version 3 expects them to be, and this particular means the image size. In the next step, we also include the top features and regions that will work against the classification, like the anti-boxer, shall we say. Here we put positive only equals false, so we use the same thing. Here we can see in red what the network thinks is most unboxer-like, and probably the grass is one of those areas. And you can see this is also something that we need to be aware of when using these image classification models, that the network really learns from everything that's in the images, right? We as humans would maybe naturally assume that we learn from the shape of the dog, but not from the background. But there are famous examples where the network has indeed just learned to discriminate between the classes from the background, but not from the image itself. Following the example in the Lime documentation, we can also express this as a heat map, and we copy over the code from there. So here we can see in blue, like the dogginess, and in red, the anti-dogginess, or in this case, the boxer rather. Of course, now we can't really see the image as such. It's more difficult to interpret, so we really should do this side by side, but we can see which region of the image are more important for the network than others. And you can see that here the head and the main part of the body of the boxer, these are the regions the network thinks are most valuable and important to create a boxer classification, whereas, for example, the background here is something that would work against.